This is a, a quick introduction to what each presenter will be presenting at the workshop or the World Congress for Human Brain Mapping in March. I've sent this list to each person. If you have of the talks, if you've not received it, let me know. But this particular Word document gives your titles and the sessions, the session number, for example, A7. And I'll be sending out the program when it's finalized so you can see which days these will be. But the goal basically is to introduce the audience to neural imaging of the EEG with the common theme of linking dysregulation of the subject's brain and their networks to their symptoms. So linking symptoms to the brain. It's something that others don't do that applied neuroscience is unique about. And Babak, the director, is also enthusiastic about that focus. So there'll be a common focus. The common focus is going to be the Neuronavigator applied to different case examples. Now, I will have a PowerPoint at the beginning of my talk, and I go first in each of our sessions. And so I'll cover some of the basics about three-dimensional imaging and what the difference is or the advantages of the Neuronavigator. Things like the boundary element method, the inverse solution, using 12,700 voxels, etc. I'll make mine just fairly quick, 5 minutes on the PowerPoint, and then I'll be going into an example of a patient. For example, my talk is on neuronavigation of functional effective connectivity. So I will have the Neuronavigator launched already and a PowerPoint already in advance of walking up to the podium. And each of you need to do the same things. Don't waste your time or the audience's time launching NeuroGuide and launching the Neuronavigator. It takes a lot of time. Instead, do that when you get in initially and have it ready to go in your laptop. Go up to the podium, bring your laptop with you, place it on the podium, connect it up, and then give a presentation, your 15-minute presentation, which again is focusing on case studies. And the whole goal here is to educate the audience about the Neuronavigator and how you can actually evaluate networks, you can evaluate dysregulated hubs, you can interface it with diffusion tensor imaging, etc. The audience is going to be mostly neurosurgeons and engineers and people that don't know much about EEG. They do know that something about MEG, and we'll be interacting with them a bit in the MEG people. That's why the title of some of these talks, like A54, is MEG/EEG. Ernesto has been able to, he's worked with MEG, and when I was at the National Institutes of Health, I also worked with MEG. I did simultaneous inverse solutions, using at that time the Neuroscan inverse solution for discrete solutions, and a little bit with Loretta. And then compared that to the MEG, and you can subtract one from the other. We're not going to get into that in great detail. Ernesto will be able to do that. In the future, we'll have a control on the Neuronavigator that one can click and switch between the MEG lead field and the EEG lead field. So it's one of the advantages of the Neuronavigator is that it uses a homogeneous lead field. That is, the lead field is a measure of the sensitivity of electrodes or the sources with respect to electrodes on the surface of the scalp. And that sensitivity for electricity is different than it is for magnetism because the scalp and the skull and ventricles and white matter and all the various heterogeneous aspects of the brain is invisible to magnetism, but it's not invisible to electricity. The different conductivities in the different tissue spaces reduces the accuracy of the EEG inverse solution. So Ernesto in 2007 was able to mathematically eliminate the heterogeneity and thereby create a homogeneous lead field like MEG has. So you can imagine that as a balloon that you fill with saline, nothing inside there except the saline. You put sensors on the surface of the balloon. That's MEG. But the Neuronavigator is like that also, which I'll show in a second. So I'm going to begin, for example, in my talk with a PowerPoint, and I'm going to you give this out when I finish it. I'm not done yet, so that you all can create your own, put your name and your affiliation, and you can have your own slide color if you want. Put your title of your talk up here. Ernesto works for Applied Neuroscience, so his should be this, should be the same as what I have here, but each of you have your own affiliations. Now, I'm going to just introduce very briefly, possible I'm not done with the slides, what the difference is between the old Loretta, low resolution electromagnetic tomography, introduced in 1994 by Roberto Pascual Marquis at the Key Institute in Switzerland, that had a heterogeneous lead field. It also had a average brain from the National Institutes of Health in Montreal of 306 individuals. That's why this is very, very smooth. You can't see anything in there, but it's a good navigation tool. It used a spherical head model. That's where you shrunk a sphere onto the skull. That has inherent limitations compared to the boundary element method. Boundary element method is where you actually go into the individual MRIs, where you can see here, which are, it's a real MRI. It's not an average. It's a single MRI. It's a template from the National Institutes of Health. And then you identify the pixels or voxels that surround a given structure, and you create a boundary. And now under Green's function from 1830, once you know the boundary around any volume, then you know what the sources are in the interior of the volume. That's how boundary element method works. So it's a whole bunch of little spheres inside the huge larger sphere being the brain, or the scalp and the skull. I'm going to quickly show what the advantages and disadvantages are. I don't know if I'll have this slide or not, but this is the inverse solution. Now, the people in the audience don't know what inverse solution is. Some of them do, some of them don't. So I'm going to introduce very, very quickly. Essentially, it's a linear equation. K is the lead field, which is a model of the scalp, and different conductivities of the skin, the skull, and the brain. And knowing these conductivities allows you to take the electrical field or electrical potential from the scalp surface, that's E, and then the solution, J, are three-dimensional currents. So this is actually E, J, and K are three-dimensional vectors in vector calculus. The solution to this equation is to move K underneath E and divide K into E to get J. So it's really J equals E divided by K. And the sensitivity is a Gaussian distribution that is used for what's called regularization. I won't go into that, but that's what the equation is. And now the key to it is the inverse solution. Is the lead field, because if you divide any quantity in vector calculus, if you've taken a course in vector calculus, any quantity, it could be 1 divided by a three-dimensional vector like K, then there's an infinite number of solutions. So you have to constrain these solutions. And the constraint on the solutions in part is the boundary element and the way that it's arranged, and the use of S Loretta. So the S is standardization. It's essentially taking the standard deviation of all the voxels and dividing that into the total volume. So, or you take the total standard deviation and divide it inside each of the voxels. That standardizes it. It helps reduce the spherical head model issue, but it also gives rise to unique solutions. That's what Roberto Pascual discovered. So we are using Loretta, but it's S Loretta with weighting being the standardization. I'm going to get rid of this slide. It's really for a more sophisticated audience. And so you can play around with this template that I'm doing. But this is what SW Loretta is. I'll probably just have 2 slides. I'll have S Loretta, and then I'll show how SW Loretta works. Essentially, you have a heterogeneous lead field in the lower left, that's L. And then there's a weighting matrix using single value decomposition that you divide or actually weight each of the voxels so that you get the what you see in the lower right, which is a homogeneous lead field, because you've now weighted the initial heterogeneous lead field with this matrix to cause it to become homogeneous. And this gives you the accuracy of the inverse solutions. A lot of this I will be taking out. I'll probably show this one because we work with binaries and hubs, and we link the networks to the connectivity that connects the hubs. And then I'll be presenting things on Parkinson's and the cerebellar circuits. And we have plenty of time to put our talks together, share them with each other, refine them so that if you're going to use the PowerPoint, it can't be more than 5 minutes because you got 15 minutes. It's got to be very short. And then you're going to spend the rest of your time with 1 or 2 sample subjects, demonstrating how you use the Neuronavigator to assess, evaluate that patient. It could be a patient with epilepsy, it could be a patient with PTSD, it could be an autism patient, whichever one is in your category that you're going to be demonstrating, and you're going to show the tools that are provided to clinicians by the Neuronavigator. So I'm not going to go into these, and I will refine this. So I've already launched my navigator. So I want to do something on epilepsy, and so each of you will have an epileptic patient, 1 or 2, in this one section here, or post-treatment evaluation. It's and diffusion tensor imaging. I'll help Richard with this one. So I'm going to just minimize this for now. I'm sitting in the audience. I go up. Now, what I've done is, when I launched my navigator, this is the demo, this is my default. So I'm going to change that. For example, I'm going to maybe go to the anxiety network, and then I'm going to go to settings. I'm going to make this a default. So now when I launch the navigator, this is what's going to come up. Now I can go here and make this the default. I prefer to use this as a default because I'm going to go to 5 Hertz. And again, I'm going to make this my default because you need to show the audience how you can navigate around the different parts of the brain. And this one has the cerebellum in it. And so you're going to have this ready to go when you come up to the podium. Plug your laptop in and have this ready to go with your patient. And you'll be able to show the audience, here's the patient's EEG, it's an epileptic discharge, or it's a person with PTSD, or whatever. And then show how you had launched the navigator, and now you're going to explore different networks. And you're going to talk about how you evaluate 1 or 2 examples. And actually, one example, if you do a good job in the navigator, it's going to take you 15 minutes to go through all the various things the navigator can do. For example, I'm going to go to volume view and let them know this is the connectome. It's a 2-dimensional view of the networks that are 3-dimensional here. I'm going to get rid of the cortex. I'm going to select the first slice. It helps to see the axial slice. I can see how you can go up and down through it. I'm going to now go to connectivity, and I'm going to select functional connectivity. And I'm going to select the center voxel. So you can, again, have this if you want as a default, but it's good to show people how you can do that. data type I've got, let's see, the connectivity is here. I have a 1.65. If you can show that as you change the z-scores, you get that to change. You can use raw scores. There's the raw scores, and you can do z-scores, and you can discuss what you do. You can then go through different networks. Say you got a person with attention deficit disorder, or it's an epileptic patient, and you want to look at the attention network. We also have the ability to do screen capture, that is time domain capture, and then we also have real-time Loretta. In the future, we have, like I said, a couple months. I'm going to be practicing and developing presentations for these different types of patients that in which I can show the networks and the different features to help you learn about it. Now, there's lag coherence. We'll be able to explain that, phase differences, information flow, etc. We also have then, and this is for Richard Abbey, but I'll also be showing it, the diffusion tensor imaging. You can do just these ones, and to need to demonstrate this is to do that, you need to expand this, and I'm going to have some ready-made files that you can bring in. Now, here you see that when you do this, that the two-dimensional connectome is not right. So I'm going to go up here and get rid of the connectome. I should be able to get rid of it. And so yeah, the problem was that was in the 4+ view. So you don't want this. This shows you too much. You're going to use the diffusion tensor imaging just like you would connectivity with the network. Now I'm going to right mouse click and under the number I'll disable all. And then I'm going to select just the cerebellum and the motor cortex, for example. Now I'm going to have a file that I'll be able to bring in. I'll be able to go to File, open a session file, and bring the file in that has what I've selected. And I'll make sure everybody has that ability as well. And then I can go down here. This is the cerebellar file. And actually under networks, right mouse click and enable all. And now I've got the cerebellum. I'm going to go to volume view. I'm going to get rid of the head model, or at least make it much more transparent. I'm going to close this down. And that way people can see what it is that we're working on. So I'm going to get rid of the head model, get rid of the cortex. So that's just the cerebellum, okay? as I mentioned, I'm going to be playing around with this, and you should practice your patients as well. I'm going to make one that has also the somatosensory cortex in it. And so let's see if we have under symptoms. Parkinsonism. If we don't, we will get them. Yep, there's Parkinsonism. Okay, that selects the sensory motor cortex and the cerebellum, the red nucleus, etc. And you can see here, I think this is information flow, that there's a lot of information flow between the deeper hubs and nodes. And there's less information flow between the hubs, between the motor cortex. There's quite a bit, and there's low information flow compared to the long distance network. You can look at that as z-scores, and we can change the z-score sensitivity. So you can see everything, and again, you can save this if you want. So you can see most of these are normal. I'm going to go to settings, and I'm going to make this as a default. So now whenever I bring up information flow, it'll have Z going from 0 to plus or minus 3 standard deviations. I know that because that's what I set it at. 0 plus or minus 3 standard deviations. I'm going to go here to coherence. And for coherence, I'm going to do the same. I'm going to set to 0. And then I'll do my settings. But there's coherence. And so you're going to have your patients that you will evaluate in this manner to show the audience the power of the Navigator. And as I mentioned, this also will include, I'll have some demos and examples of how to use the screen capture or the time domain capture tool, how to use the real-time Neuronavigator, that is, you have EEG and a movie running across the screen, and you'll be able to show how the Neuronavigator works in real time. Those are the things. There's 3 parts to the Neuronavigators. There's this one for assessment. There's the other one for epileptic focus. You want to identify what's going on in a given location and how that particular part of the brain is not working right, or it is. You use the time domain capture. And then you can assess also in real time, which gives you an intro into neurofeedback, because we do SW Loretta neurofeedback by reinforcing greater stability and efficiency in the hubs. And so you're able to show those 3 aspects, as well as being able to show things like the scalp map here, the head model, cortex, etc. So people will get a view of what's going on, what's available for them to purchase, actually, and to use in their practice. That's the big thing that we're trying to introduce, but Beck wants to introduce, he's putting a lot of money into MEG. Each MEG $1 million to $2 million, 20,000 a month for liquid helium. And we're able, and it cannot measure sources from the cerebellum. So we're able to introduce this as something to complement their plans for MEG, which they've already got installed all around the world at a fraction of the cost. But Beck actually wants us to raise our prices a little bit. But once they are able to see this and how it can be applied, it's going to educate the audience and will enhance the field of quantitative EEG, because they kind of look down upon EEG. American Academy of Neurology has condemned the use of it, etc. So but neurosurgeons are free of this dogma, pretty much, that the neurologists have imposed as turf battles have evolved, and they want to control the entire universe of EEG. So anyway, this is an example of what you'll be doing with the Navigator for case studies. You may or may not need a PowerPoint, or if you do, just 1 or 2 slides. because what you really want to demonstrate is the practical application of the Neuronavigator in your own practice and with case studies. That includes diffusion tensor imaging, which we can play around with as well. See if I can do that. But again, there's no hurry. So here's diffusion tensor imaging. To see it, you need to get rid of the skull, and cortex. But this will be very impressive for them to be able to see. Now, these are z-scores of the Neuronavigator of diffusion tensor imaging. It happens to be coherence. And the way this works is the endpoints, the Brodmann areas where these fibers terminate, are colored depending upon the deviation from normal. So if it's red, that means there's a lot of deviation from normal. You can see in the right hemisphere. It's blue in the left hemisphere. There's low connectivity there. And we can then look at different data types. And here's information flow. There's much less information flow in the right hemisphere, whereas damage is. And so these are the kinds of things that you'll play around with and practice in advance of coming to the meeting. So you can just take one or two exemplar patients that you have, and I have plenty of subjects if you don't have any, and then demonstrate it to the audience. So I'm going to close this off for now, and we'll be having more of these discussions in the future.